Welcome everyone. We're starting just because there is no more room in this hall, auditorium. It seems like today's presentations are very popular. We just heard an excellent colloquium by Douglas Scott, who is sitting somewhere over there. And if there is any 5 sigma result from Planck, it's Douglas' presentation. Quite unusual and original, and I must say a pleasure to hear every time. And we also have other visitors that you may recognize, Martin White and Jan Kohn, visiting us from sunny California. You can get a sense for how it is work in the South Pole, just by visiting us. And also Raja Guhathakurta is visiting us from UC Santa Cruz. We hope to see him in the future since his daughter is shopping for a school in the area. And so we hope that this is not the last, but actually the first in a long series of visits. So we will start the lunch with a presentation by Raja entitled Looking at and Through the Milky Way. And then we'll hear again from Douglas, who will talk about our motion through the universe. And then we'll hear from the colloquium speaker, Carlos Badenes, who is over there, from Pittsburgh, and he will tell us about the progenitors and lifetimes of planetary nebula. And finally, we'll hear from Martin White on cosmology in one dimension.
Will we have questions at the end, or questions at the end of each speaker?
Questions at the end. So I should mention that usually we have an ITC presentation first, so that it sets the stage. And the disadvantage of that is that our members speak longer than 10 minutes. So today we have Raja speaking first. So we will ask you questions after you finish, after 10 minutes.
He asked you questions before he began.
And will you give me a warning?
Yes, you will hear the buzzer.
Okay, perfect. So I'm going to talk about looking at and through the Milky Way. And this is really about a little discovery on my part. I've been studying distant galaxies for many years. I've been studying the Andromeda galaxy for a long time as well. And only just came to the realization that I live in a galaxy. So I've sort of turned things around a little bit to say, instead of looking at the things beyond the Milky Way, let me look at the Milky Way. But at the same time, let's not waste all that good real estate on the spectrograph or on the CCD. So wherever there's room between the stars, we look right through the Milky Way at things beyond. So that's going to be the theme. And I'll start with the study that got me into this kind of thinking and this kind of study. And this is a study of one of my favorite galaxies in the whole world, Andromeda. These are 3 sight lines through the spheroid, whatever that means, disk, and giant stream in Andromeda. These color magnitude diagrams, or this flavor of color magnitude diagrams should be very familiar to the audience. You see a red giant branch, you see a red clump. Is there a pointer I could use?
There's one there.
Oh, perfect. Thank you. So this is the red clump right there, each of the 3 lines of sight. This is the lower part of the giant branch. Things get quite noisy at the main sequence turnoff. And this is a real scale. These are magnitudes here. These are faint stars, because these are turnoff stars of the distance of Andromeda. So this is something like 100 orbits with Hubble's Advanced Camera for Surveys. So, Tom Brown was the leader of this study. But in this color magnitude diagram, what you can't see very easily, unless they're highlighted like this, are these stars that are fairly blue, that have roughly the same color as M31's turnoff, but they're much brighter. They're, of course, turnoff stars in the Milky Way's halo. So we decided to take advantage of the fact that we had deep images in these fields to go back and take a second image in these fields, something like 5 years after the original exposures. In those 5 years, stars move across the sky relative to distant galaxies, and we are able to measure that motion. So that's what this next slide is about. So this is proper motion now in milliarc seconds per year. And you can see that the stars that are in this circle here are Andromeda stars. They have, because of their distance, they have very small proper motion, small but measurable, distinct from zero, at least as an ensemble average. And the blue symbols here are halo stars in the Milky Way. The gray symbols in the back are what you might expect from sort of a standard, something like a Besenstein model of the Milky Way. I should pause I should sort of digress for a minute to tell you how remarkable this sort of measurement is with Hubble. We're talking about remarkable precision. We're talking about measuring things down to something like 1,000th of a pixel. It is quite literally like watching human hair grow on the moon. Okay. It's exactly that rate. Someone had a lot of time on their hands figured this out. But this is, you need a 5-year baseline. You need at least a 5-year baseline. And you need one of the epochs to be deep, because what we're doing is we're using background galaxies in the universe as this cosmic wallpaper against which to watch these stars crawl across. Crawl is the appropriate word. They're not moving fast. And here's a little sort of cartoon that NASA put together. There's the Milky Way. You can see Andromeda in the picture there. And after NASA finishes labeling all the constellations, we will zoom in. And you'll get a sense of the kind of measurements we're talking about. So we're going to zoom all the way in till you see a tiny field along the minor axis of Andromeda. This is a single ACS pointing, Advanced Camera for Survey. A single pointing is 3.5 arc minutes by 3.5 arc minutes. There it is, right there. We're going to zoom into that. And, and then we'll watch the years go by, okay? We started in 2002. And if you wait long enough, you'll see that the stars move relative to galaxies. So that's what this is the simulation of how the Andromeda stars would move. This is very, very subtle. The Milky Way star motion is something like 10 times less subtle than this, because they're about 10 times closer. We're talking about 100 kiloparsecs versus 1,000 kiloparsecs for Andromeda, so 100 kiloparsecs for Milky Way stars. Okay, so using data like these, Alice Deason, a couple of years ago, looked at a bunch of stars in the direction of Andromeda. NASA loves these cartoons, so here we go. Stars in the direction of Andromeda. There's the Hubble. It's in a very large orbit around the... but anyway, to scale, exactly. The main measurement in this was we found that while the anisotropy in the Milky Way halo in the solar neighborhood is such that stars are moving predominantly radially, that's no longer the case once you go out about 30 kiloparsecs, at least in the direction of Andromeda. Things look roughly spherical. The radial velocity dispersion and the tangential velocity dispersion are roughly equal. And if you look at it a little more closely, what happens is the tangential velocity dispersion has stayed about the same between the solar neighborhood and 30 kiloparsecs from the center, sorry. And the radial velocity dispersion is what's dropped. And so we looked at this and said, this looks something like a shell. And if you look at color magnitude diagrams in this direction, there's evidence that there is a concentration of stars at a common distance, about this distance. And this even has a name. It's called Tri-An, Tri for triangulum, An for Andromeda. So it occupies a large chunk of the sky. And this is a very messy plot from another paper by Alice last year. And you can see various concentrations in RA deck space. And there are some interesting velocity gradients across this. I won't go into the details of this. I'll just show you some of the trash from our SPLASH survey. Our SPLASH survey is a spectroscopic and photometric landscape of Andromeda's stellar halo. But the trash from that, the foreground trash from that, is something that we pulled out of the bin. Fortunately, it was in the recycling bin. We pulled it out. And you can see there's a velocity spike in addition to a dynamically hot component. And this velocity spike is presumably associated with some of these substructures here. I'm not going to go into the details of this, but it's clear that the velocity kinematic substructures associated with the spatial substructure. So sort of inspired by this, I said this is, time to really put a lot of emphasis on our foreground stars in the Milky Way halo. Instead of, let's turn the tables. Let's look at the Milky Way and let everything else be incidental. So that's been the main focus of this. We've taken deep HST images that have been, typically these images have been taken for the distant galaxies in these fields. But if it's deep and if it's multi-epoch, we can use the distant galaxies, we can abuse the distant galaxies, we can just use them as wallpaper and watch the stars, about 1,000 main sequence stars, crawl across the face of these galaxies along many different lines of sight. Wherever Hubble has taken at least one deep image and at least a second image that's separated by 5 or 10 years, we consider those fields fair game. So this is a big archival program. And to sort of complement this, we have a Keck spectroscopy program where we want to get good spectra of these really faint stars. These are main sequence stars that range in brightness from 21 in V to 24 in V. So fairly faint. They're relatively high temperature, unlike red giants. They're relatively high temperature. So the lines are not that strong. The absorption lines are not that strong. So the combination requires very deep integrations. We're working in some of the familiar fields. Many of you know the candles fields. These are Goods North, Cosmos, and the extended growth strip. These are fields that are well known because of distant galaxy studies. And we're doing anywhere from 8 to 32-hour integrations with the Keck telescope of, in the end, our sample size should be about 350 Milky Way halo stars, main sequence turn-off stars, ranging in distance from 20 to 150 kiloparsecs. We expect to measure radial velocities, chemical abundances. The line of sight distance will be the most uncertain, and we expect to treat that statistically because once a star has a color that's slightly redder than the turn-off, it could either be on the main sequence or it could be on the subgiant or lower giant branch, and so we want to model that. We want to measure chemical abundances. We've been calling this the 7D survey because there's 3 spatial dimensions, there's 3 velocity dimensions, and chemistry is what we're treating as the 7th dimension. Now, just by chance, we're also going to get exquisite spectra of distant galaxies. So Charlie's working with us Charlie's working on a set of quiescent galaxies for which he studies stellar populations. David Koo, Sandy Faber are looking at, and their postdocs and students are looking at outflows in star-forming galaxies. So just a quick sample. The very first spectrum I pulled out was not a star, it was a quasar. I was beating my head against the wall thinking all of our objects are going to be quasars, but it turns out this was the only one on that mask out of 20. Most of them look like this. This is perfectly boring. It's a spectrum of a star. Some of the features you see here are instrumental features or atmospheric features. Like this is an atmospheric absorption line. This big ball here is an instrumental feature in the spectrograph. But if we zoom in on that feature there, I'll show you, zoom into that for 3 stars, and you can see that this is the magnesium triplet. It's very strong in one of our 3 stars, slightly weaker in another one, practically non-existent in the other. So I'm just showing you that there's some diagnostic power here to measure the magnesium abundance in these stars. You can do the same thing for calcium, and this weak line over here is an iron line, but these 3 are the famous calcium triplet. This is our sort of chart of signal to noise versus brightness. We expect to measure velocities above this signal to noise level, so practically for our full sample we'll get radial velocities, and we'll get chemical abundances for about half our sample. Okay. Now, this is just an example of our filler background science. These are M31 red giant stars that happen to be in the background in some of our fields, and we get exquisite quality spectra of these stars. Put this in perspective, there are 4 stars for which alpha over Fe has been measured in the Andromeda halo. We should increase this by 2 orders of magnitude, and this data set is reduced. So, in summary, we're measuring proper motions, radial velocity, line of sight distance not so well, but chemistry of stars in the outer halo. We expect to turn this into dynamical mass estimates of the Milky Way and learn about its accretion history. In particular, looking at satellites or disrupted satellites of dwarf galaxies is proving to be quite an interesting aspect. Andromeda red giants, we should have chemical abundance measurements of really high quality. And there are 2 distant galaxy projects that we've concentrated on for our filler science. And that's where I'll stop. Thank you. That's a shell looks more likely. There isn't very strong spatial structure to this thing. It also, if you look at the details of the velocity dispersion of the structure, it's not that cold. It may not even be one satellite. If there's a characteristic energy for satellites falling in, you could imagine this to be sort of, in a way, a statistical feature of the halo. This may be related to things like breaks in the profiles of galaxy halos. So the jury's out. We don't know, but we're going to look at this more closely. Other people will too.
So, Raja, I might have missed this. You talked about the tangential velocity dispersion.
Mm-hmm.
Is there also a mean proper motion, some rotation in the shell?
We are fitting for that. Oh, for the shell, it's a small, relatively small. It's consistent with zero. We do fit for that we do fit for the mean velocity and the dispersion. So there isn't, at least there isn't a very rapid rotation. There isn't a significant or rapid rotation that's coming out of this data so far. But we've only looked at a dozen stars in the thing that we've looked at so far. We should increase the numbers a lot soon.
Wouldn't we expect some rotational velocity for any kind of confined structure like this?
That's right. I mean, that's right. The chances of it being a purely radial thing are very small. That's absolutely right. But, our limits are not that stringent. I think we can't rule out something like 50 kilometers per second for the rotation. So, and compare that to the dispersion of something like 100 to 150. So that's sort of the range of numbers we're talking about. I've been asked to give you this. That's the laser thing.
Don't forget the microphone.
Mark, if you have 32-hour explosions, you need a bigger telescope.
So we're trying to build one. Yeah. So are you. Yeah. No. Well, that's the best way to get ready for a bigger telescope.
Okay, is this on? Okay, so now for something completely different. Let me just put that in my pocket. So I think it's well known that there's a dipole in the cosmic microwave background. So here are pictures from the COBE satellite. It turns out both WMAP and Planck, when they measure the dipole while they're making maps, so they actually there aren't maps showing the Planck dipole. So I could take a Planck map and add the dipole and show you that, but I haven't. So here's the COBE dipole. So this sort of yin and yang shaped pattern, this is the galaxy. These are images of the whole sky. I hope everybody understands that. We are moving towards a particular direction in the sky up here, in which all the CMB photons are hotter and therefore redder in this picture, and away from a direction over here. It's also well known that the CMB has a monopole, which is very strong. So if you just plot the whole CMB sky, it looks like, well, it's green on this color scale, but the monopole for the CMB is, the best fit number is 2.7255 plus or minus about 6 in that last decimal place. So that's still the best known number among the cosmological parameters. So well known that we usually fix this. It's actually the 7th cosmological parameter, but normally we say that there are 6 because we fix this guy. CMB last scattering surface defines a rest frame through which you could be moving in order to see a dipole. That rest frame is the frame in which there's no dipole. So this often makes people, well, even physics professors, but certainly undergraduates, uncomfortable because they think they just learned that there are no preferred frames in the universe. But there is. There is a special frame in the universe. It's the frame with no dipole. What you actually learned in special relativity class is that there are no special frames for doing physics experiments. The laws of physics are the same in all frames. So that is true here, except, well, for one thing, this is cosmology, so it's general relativity and not special relativity. So it's allowed to be a little bit different because you're talking about the whole universe. But actually, this rest frame is only special for one physics experiment, which is measuring the dipole. So we could get together with alien civilizations and agree on the rest frame of the universe. So there is a rest frame of the universe. And it's the one in which the whole sky appears to be just green like this. If we're moving relative to that rest frame, then we will see a dipole. It turns out that when we make that measurement, we're moving at about 370 kilometers a second in a particular direction. That's a combination of our motion around the Milky Way, which I guess is the overlap with the last talk. The Milky Way is moving towards Andromeda, which is Raja's favorite galaxy. And the local group is moving towards Virgo, and Virgo's doing its thing. When you add all that together, you get this velocity in a particular direction. It turns out with the new Planck values, I just worked this out last night, the value of beta, which is v over c, is we are moving at 0.12345% of the speed of light. And it's working at stuff like that makes the universe worth living in, if you ask me. It all makes everything worthwhile. Towards a place in the constellation Crater, if you ever wanted to know why Crater was a big deal constellation, but then there are other effects which I'll show you in a second. Here's my map with some constellations in. We're moving there, right? So sometimes people say that it's Leo, but I worked this out just to be absolutely clear with the new dipole and so on. So it's definitely just inside the constellation Crater. That is the cosmic dipole direction. It is a special direction on the sky, which is everybody should know about. Mostly they don't. There's a bunch of different things that happen when you boost frames. So one of them that's the best known is the dipole. The better way to think about the dipole is that you're boosting the monopole. So the fact that there's a monopole of a certain temperature and there's a velocity beta, which is 0.12345% of the speed of light, gives you a dipole which is in the millikelvin range. But as well as boosting the monopole, we also boost all the other multipoles. And this is a thing that's new and was just measured by Planck. So you will modulate all the anisotropies. As well as that, you aberrate the sky, which I'll talk more about in a second. You increase the monopole when you boost frames by a small amount. And you also introduce a kinematic quadrupole. So I'm going to talk for the last few minutes about these two guys. The first one, as I said, is well known. This is unmeasurable. I mean, in some sense, it means that the CMB monopole that we measure is not the monopole, but the monopole in our frame. And this one is probably too hard to measure, but in fact is taken out of the Planck data. So the only way to measure it in the Planck data would be to put it in and then measure it. And then you'd have to convince people that that was okay, right? So you can run through the math, right? If you want to boost frames, you can boost the temperature to a new frame. Okay, you change the direction, you expand to first order in beta, you get a big messy thing, but this is the dipole. These are deflections of the rays caused by your motion through the sea of CMB photons, and this is the modulation of all the anisotropies. So to see that a little better on the sky, here is a simulation of the CMB sky, aberrated with a really high beta, so we would be moving really fast. So one side of the sky, all the spots get brighter. The other side of the sky, they get fainter. And here, all the spots get bigger or smaller. Oh, the other way around. For reasons that aren't entirely clear, I did this on an egg. I think maybe it was Easter when I made this. I don't remember. So, this is aberration, and this is modulation. So when you're doing introductory special relativity classes and you talk about running into the rain and so on, right, then it turns out that the CMB is a great example of that now, right? So we have now detected both of these with Planck. So it is possible with Planck to measure both the aberration and the boosting effects. you can do this either in map space or harmonic space. We actually use harmonic space because it uses the full machinery of correlating scales, which is effectively what's happening. So you need 4-point functions, and there's a whole bunch of machinery to do that for lensing and non-Gaussianity. It's the same machinery. It's a little easier to understand in to think about how you would do this in map space. So here's the usual CMB anisotropy power spectrum. So what's basically happening is if you chose the part of the sky in the direction we're moving, then all the anisotropies are brighter, and they're also on smaller scales because they're all shrunk. So the whole power spectrum will move diagonally in this way. So if you imagine taking the quarter of the sky that's where we're moving, then it would be like this, and the other quarter of the sky would be like this, and then, ignore the half the sky that's in the equator, if you like. So you could do it that way. And in fact, that's not what we do, because you realize that this dipole modulation couples L to L plus or minus 1. So this is a simple quantum mechanics thing, which some of us might remember. So if I take some multiple moments, I multiply that by a dipole, I get this map, and this map contains the original dipole moments, but also the something which is lower by 1L and higher by 1L. So in other words, by multiplying by a dipole, I've mixed L with L plus 1 and L minus 1. And I could do that with, I could rotate. The special direction wasn't important. So multiplying by a dipole means coupling L to L plus or minus 1. So what you actually do is work out a statistical technique where you don't do that power spectrum shifting up and down diagonally. You look at all the multiple moments, and you look for the coupling of L to L plus or minus 1. So what? So I'm not going to show you data and stuff because it just shows that we've detected this. So both these effects are detected at about the 4 or 5 sigma level. So there's a complication here. There's a hemispheric asymmetry at low L in a different direction. This dominates the signal at high L. So there's not very much signal comes from low L. So there's a complication there for anybody who's interested in statistical anisotropy in the maps. It slightly biases the parameters, because what's really happening is in every little direction on the sky, the parameters are slightly different than you expected because of this boosting. And it means if you have an experiment that just does this little bit of the sky, and you do it really, really precisely, then you better be aware of the fact that you're measuring the wrong parameters. Fourthly, maybe, it doesn't really tell us anything new, but it's definitely cute. So when you're discussing running into the rain, right, and you want a nice example, you can use the CMB sky. The hotspots on one side of the sky are genuinely smaller and brighter than they are on the other side of the sky, and that has been measured relative to the CMB rest frame. It was only really possible to do with Planck. I was going to say something else there, but I'd completely forgotten what I'm going to say, so let me just let Galileo have the last word. So this is, didn't have the last word. So I think this was Martin's idea. Was this Martin's idea? To name the paper E pur si muove. So it's the only Planck paper with a goofy title. And the reason is because it's Italian, and half the Planck people are Italian, and you say, can I have this goofy title? And they go, oh, Italian, that's good. It's all good. So basically all that we've done is a really poor measurement of the dipole, but with 2 completely new physical effects. And as I said, it makes it really nice when you're trying to explain running into the rain, and you're talking about special relativity, and you explain aberration, and this is a nice version. When you think about it, actually, we originally called this special relativistic effects in the CMB, but this isn't special relativity. Because does anybody know when was aberration discovered? And in what century was it explained? It was explained in the 18th century, right? So if they'd been really smart, they would have derived special relativity from the explanation. It requires that the speed of light is constant for everybody. And to most of us, that means special relativity, but actually that was the explanation written down by the same guy who discovered it about 3 years later. He was a smart guy. Anyway, so let me finish there. Yeah.
There is an effect of the same order that could also be included, and that's of course the fact that we see the gravitational potential
Yeah.
in the Milky Way, which is also beta squared order, the same
Yeah.
magnitude.
Yeah. And there's other lensing effects that haven't been fully calculated actually, right, as well. Yeah. And because we sit in the galaxy, there's also LL plus 1 coupling caused by the fact that we're not in the center of the galaxy, right? So there's a dipole of the potential which you could factor in actually. That's really small though.
I'm just curious, how precise is the velocity vector for the size of the error bar?
For this new thing, the new thing is 4 or 5 sigma detection, so that's big error bars, right? The dipole itself is measured really quite precisely. I mean, it's uncertain in the 5th decimal place. So it's 0.12345% of the speed of light, but the 5 is the central value. There's an error bar in there.
Is this on? Should be on, right? Okay. Let's put this here. Oops. I'll just put it in my pocket. I'm afraid I broke it. Okay. Nothing happening? Oh, there we go. Okay. Slideshow. Here's the pointer. Okay, great. So I'm going to tell you about a paper that appeared on AstroPH a couple of weeks ago. It's called The Progenitors and Lifetimes of Planetary Nebulae. It's something I've done with Dan Maus and Robin Chardulo. I know what you're thinking of. I know the answer to this one, right? We know what the progenitors of planetary nebulae are because, well, I guess many of you, as I do, teach this introduction to astronomy classes, and then we tell this young and impressionable students that in a sun-like star, when it gets to the end of its AGB phase, it loses mass very rapidly. At the same time, the stellar core is exposed. It's very hot. There's photoionization, and that's what makes a planetary nebula, right? Amplification of a complex reality, right? And planetary nebulae are not simple objects. They have a lot of structure. And we know that this simple picture breaks down when you really try to explain the details of planetary nebula morphology, planetary nebulae birth rates. There's a lot of discussion in the community about what are the physical mechanisms to actually make planetary nebulae, whether all stars make planetary nebulae or some stars do this more efficiently than others. And our contribution to this discussion is to bring in essentially what's the ultimate test of progenitor scenarios in stellar astrophysics, which is to calculate a delay time distribution. It's a very simple concept. If you have a hypothetical brief burst of star formation, and then you record the rate of formation of whatever object you're interested in as a function of time, that is the delay time distribution. In signal processing, it's called Green's function of the impulse response of the system. And the reason we're interested in this for stellar astrophysics is because it fully characterizes the evolutionary timescales of the progenitors, whatever it is that you're looking at. This is used very often for type 1a supernovae because, well, we don't know what the progenitors of those are, and I'll be talking about it this afternoon, but it's a general concept. You can apply it to whatever you want. Of course, the trick in measuring this is that, well, galaxies don't really behave like that. Galaxies have complex star formation histories that we usually represent as a function of look-back time, and they can look like whatever you want. The convolution of this star formation history with a delay time distribution gives you the rate of the objects now. And this is essentially what you measure. So in order to recover the delay time distribution and do the constraining of stellar progenitor scenarios for whatever it is that you're interested in, you need to be able to measure star formation histories to some accuracy, and you need to be able to measure the rate, present formation rate of these objects in a number of different environments. And this is what people who calculate type 1a supernova delay time distributions do. Of course, you can also do this in the local group for things that are not supernovae. And in particular, for planetary nebulae, it's an interesting problem to tackle because you need two things: good star formation histories and highly complete catalogs. I say highly complete and not complete because, well, you all know that complete catalogs do not exist. They belong in fairy tales with unicorns and dragons and low-calorie beer that actually tastes good. But if you're looking at planetary nebula populations in some place like the LMC, you can work with wonderful catalogs. Like this catalog from Braden Parker has 442 planetary nebulae and has a spectra for each and every one of them. So it's very pure. There are very few interlopers in this catalog. The other aspect of this, and this is where it gets really wonderful to get to work in the local group. The LMC has a resolved stellar population. You can actually see the stars, and you can calculate the star formation histories in different parts of the LMC with color magnitude diagrams like the ones that Roger was showing. And this has been done by Harrison Zaritsky, and there are over 20 million stars in the Magellanic Clouds Photometric Survey that they used to do this. And one thing I like to refer to this as stellar age distributions instead of star formation histories, because star formation history leads to a bit of a misconception. We neither know nor care where the stars were actually formed. We just want to know for each location in the LMC what is the distribution of ages of those stars. And this is the data set that I was talking to you about. Have 16 time bins. And this is a three-dimensional data set. You have right ascension, declination, and look-back time. And this tells you what's the distribution of ages of all the stars in the different locations of the LMC. You have this plus that. You can get a delay time distribution for planetary nebulae. And this is what we did. I'm going to show you the results in a minute. But first, I want to do something a little more qualitative. Just look at it by eye, right? So what I'm showing you here, the red crosses are the planetary nebulae, and they're the same in all the panels. And these 6 panels are the density of stars in different age bins. You can think of this times as main sequence lifetimes. 0 to 35 million years, 35 to 800, 0.8 to 2 gigayears, 2 to 5, 5 to 8, and more than 8. Okay? So basically I'm taking this data set and I'm binning it. And I have to bin it because I only have 442 planetary nebulae. And what you're seeing is how the position of the planetary nebulae compares with the position of the stars in that age range. You immediately see, for instance, that young stars probably don't make planetary nebulae very well. We know that from fundamental stellar evolution. And you see that some age bins seem to correlate with the planetary nebula distribution better than others, right? But of course, you don't want to do it like this. You want to take the statistical uncertainties into account and the uncertainties in the stellar age distribution into account properly. And if you do that, this is what you get. So this is the delay time distribution of planetary nebulae in the LMC. So as a function of the main sequence lifetime of stars, this is the rate at which they are forming planetary nebulae. And the reason we've had this result for now over a year. The reason it took us so long to publish it is that at first we thought it was wrong. It's not what we were expecting. For some reason, stars between 5 and 8 gigayears old make planetary nebulae at a very high rate. And it's a very significant detection of a planetary nebula population between 5 and 8 gigayears. Upper limits in all other bins except for a not so significant detection of progenitors ages between 35 and 800 million years. So these are 2 disjoint populations of progenitors, young and old. Moreover, because we know, or you can calculate from simple arguments, the rate at which stars from a coeval stellar population leave the main sequence, you can divide this number by that, and you get the lifetime of the planetary nebulae. How long do the planetary nebulae stay visible for? You can do this because you account for all the stars that are making the planetary nebulae, and you count the planetary nebulae. So if you have 400 planetary nebulae in the LMC, that is telling you something about how long they live for. And again, you get lifetimes of around 25,000 years for the older population, or around 10,000 years for the younger population. And this is really very hard to explain if you only have one way of making planetary nebulae, because the lifetimes of the progenitors are very different, and the main sequence lifetimes of the progenitors are very different, and the duration of the planetary nebulae is very different too. Of course, these times translate to stellar mass ranges, so this bin corresponds to 8.2 to 2.1 0H main sequence solar masses at LMC metallicity, and that H range is 1.2 to 1.0. And these are the numbers and upper limits that we get. That's pretty much it. That's the paper. This is just from the abstract. Again, we find that most planetary nebula progenitors have main sequence lifetimes in a narrow range between 5 and 8 years. This corresponds to masses between 1.2 and 1 solar masses, and they produce planetary nebulae that live that long. And then tentative detection of a second population of planetary nebula progenitors. And one thing that I find very puzzling is what's happening in between. Right? Because we know that these stars go through an AGB phase of some kind. They just don't seem to be very good at making planetary nebulae. That's basically all I have to say, but I want to show you one more thing, because this technique is really general. You can apply this to anything that you can catalog in the LMC and compare to the underlying stellar population. And some of those comparisons are actually quite interesting. For instance, this is the delay time distribution of variable stars, Cepheid variables, R. Lyrae, and Delta Scuti. And I did this with the Ogle catalog. And here you don't have to do any binning because you have several thousands of each of these stars in the LMC. And you can see it's really very beautiful how the Cepheid variables have young progenitors and the R. Lyrae have older progenitors. The Delta Scuti seem to decay a little bit. And you may again say, well, we knew this already, but I don't know. If you take stellar evolution models that literally, I may paraphrase Darth Vader and say that I like your excessive faith disturbing. This is for high-mass X-ray binaries in the SMC. This is something I'm doing with Andreas Zezes and Vali Antoniou, who's here somewhere. And this is for supernovae. This is the original paper Dan Maus and I published in 2010. But it is, I think, a very versatile technique to really test stellar evolution in a regime where you actually have a lot of data to do that with. Thank you very much. Well, that's a very interesting question. So when we posted the paper in AstroPH, there was a lot of mixed reaction. Most people were very positive because, again, this is a statistical measurement. Of course, people have estimated the lifetime of the progenitors of individual planetary nebulae before. You can do this by looking at the cores, for instance, but not for the entire population. And I don't really think anybody was expecting this. The reason I explained the delay time, I took some time to explain the concept of delay time distribution, is because I found that it's hard for people to grasp that in detail somehow. Probably because they still think of star formation histories. And of course, this is several dozen disk crossing times. The stellar populations are mixed. You don't know where those stars were formed, but you don't care. As long as you know where they are now, those are the stars that are making the planetary nebulae or the X-ray binaries or the supernovae now. Okay? A couple of people who do planetary nebula models I know are interested in following this up, because especially the lifetimes are very useful. This has something to do with the photoionization and the escape velocity of the material. Yes. No, actually, the people who do the most complete photoionization hydrodynamics models, which is really what you have to do, these timescales are right on the ballpark of what they find for single star models. Now, this is a bit speculative because we don't have morphology information on all these planetary nebulae. You need HST in order to get that information, and we don't have it for the whole 442 planetary nebulae. But in the Milky Way, bipolar planetary nebulae have a larger scale height. A smaller scale height than symmetrical planetary nebulae. And people speculate that they probably do have younger progenitors because of this. Well, if that is true, it would be very tempting to connect, this population with symmetrical and that population with bipolar. But we can't really do that, not with what we know. Yes?
Going back to your bi-eye plot.
Yep.
It's striking how the third panel is different from the one before and after it.
Yeah, these are, actually, if you read the papers, the original papers by Denis Zaretsky and Jason Harris on this, they talk about the LMC bar in great detail. It's the most prominent structure here. And this has to do with the thin versus thick bar and how you define this. That it is all spatially located in a similar place, but as you say, the details of this are different. The details of exactly where the populations are different.
Is the bimodality of the bar in age somehow related to what you see?
Well, as you can see, even if you forget about the stellar populations, the planetary nebulae are related to the bar. They appear to be very specifically related to the bar. The details of the star formation history or the stellar age distribution should be irrelevant to this. They are treated as a nuisance parameter in the analysis, right? So I think, no, it should. Oh, and I should also give you the microphone. There you go. You have a pocket to put it in?
I'm good. Okay, well, thank you. I'm going to talk about cosmology in one dimension, and I'll describe what that is in just a second. This is work that I've been doing with Matt McQuinn, who many of you may remember, former graduate student here, extraordinarily talented theorist, who's just recently started a faculty job at the University of Washington. There's another Harvard connection here for those of you who are paying attention. I'll try and give some motivation for what we've been looking at. This is a project we've been working on for about the last 18 months or so. And it's really motivated by the fact that over the last 5 or maybe 10 years, there's been an enormous literature and a lot of work on studying perturbation theory, analytic methods for understanding the formation and evolution of large-scale structure. There's been lots of new approaches, lots of new resummation schemes, ideas borrowed from fluid mechanics, quantum field theory, all kinds of other areas of physics. And at the same time, a growing appreciation of the limitations of what we have in hand right now. And it's not probably too difficult to say that these ideas aren't immediately obvious to the casual reader, and not all of the papers are infinitely clearly written. And so we've been trying to understand these developments, and whenever you're trying to understand something, the idea is to find the simplest toy model that at least keeps some of the physics intact. And so we came up with this very simple model. We weren't the first people to come up with it, but we thought of investigating it in some detail. So we have a collection of uniform, infinite, uniform density, parallel, two-dimensional sheets of matter moving along a one-dimensional axis. I'll show you the pretty picture in just a second. And the reason for that is because the problem then becomes a simple one-dimensional problem. Simple one-dimensional problems are much, much easier to solve. There's zero angles in the problem, so that's nice. One of the things we figured out about a year ago was that you can do what's known as standard perturbation theory, the kind of nominal thing you read in books, to infinite order, and you can do it with a simple one-dimensional integral, so that's really, really nice. For those of you who do numerical simulations, it's ridiculous, the kind of linear dynamic range you can get in 1D with an FFT. It's really fantastic. So this really literally runs on this laptop in, seconds. And this wouldn't be interesting or relevant except for the fact that a huge number of the features that people discuss and argue and worry about in these three-dimensional problems have extraordinarily close analogs in this one-dimensional problem. And so you can ask, well, how does this work in my problem? Are these claims that people are making correct, incorrect, misleading, whatever? So the setup is entirely trivial. I have these sheets. They're just moving back and forth across the page there. And I'll have some initial power spectrum of perturbations. They're moving around. They're gravitating with each other. And I want to understand the evolution of that system. And the thing that makes this really easy is, if you remember probably best from electromagnetism, the gravitational force on a sheet that's infinite is independent of the distance from the sheet. Right? This is probably something you measure much better in EM, but it's also true in gravity, of course. And so that actually means that you can do this perturbation theory essentially exactly. And so that's a really, really great simplification, of course. So what you normally do is you'll calculate some quantity. The standard thing that a cosmologist would do is they calculate a power spectrum. And so the one-loop power spectrum would look like sort of a linear order term plus quadratic terms that come in these various forms. And the structure in one dimension is that, it's linear plus an integral of a product plus a product times an integral. The next order term would have 3p of k's, 4p of k's, 5p of k's, and so on. And then these mode coupling kernels are just ratios of k vectors. And this structure is identical to what you see in 3 dimensions. And so many of the things that you would normally deal with in 3D have these very close analogs. It's kind of easier to see what's happening physically if you take the Fourier transform of this expression, and you just can map the terms. This one goes to this one goes down to this one, these two terms go down to this one. The correlation function has some linear piece. Growth in nonlinear gravity is accelerated, so there's a term that comes in quadratically. You can kind of think of really large scale modes as being like universes with a positive or a negative curvature. So they give you shifts in features in your correlation function. There's some kind of dispersion as things move around. And so that couples with the second derivative and so on and so forth. People who study baryon acoustic oscillations spend a lot of time studying these terms because this shifts the BAO peak. This broadens the BAO peak. And so you come up with schemes to try and undo these shifts or these broadenings. There's a lot of other things that people discuss in the literature, things known as supersample covariance, beat coupling. There's lots and lots of ideas and things that people appeal to these perturbation theories to try and understand and explain. My point is not to go through these, but to try and talk a little bit about the limitations and some of the things that we've been finding. And one of the things that's been known about perturbation theory forever is that if you take the so-called SPT, standard perturbation theory, the convergence of that series is actually quite slow, and we understand that to some extent. So people for the last 10, 15 years have been coming up with ways of resumming this series, but of course you can't resum the entire series because that's equivalent to solving the problem. And so they resum parts of the series that they think they have under control. And one of the problems is that this tends to break some of the symmetries inherent in the theory. That's very easy to see in one dimension. It's actually quite challenging to see in 3 dimension. The other thing is that the solutions are really only valid prior to when these sheets cross, because at that point your densities become infinite, and any perturbative expansion will break down. And the other thing, which is kind of easy to see from this expression, is that this integral goes all the way up to k of infinity and involves sort of p at k of infinity, which could be highly nonlinear. So I'm summing terms which are really not under perturbative control at all, and so there's questions about just what does it even mean to write down this perturbation theory. So before I show you how we've managed to make progress with this, I want to make a very brief digression on how to do this in the Lagrangian formulation of field theory rather than the Eulerian one. And in Lagrangian space, you start at some initial position q, and you move by some distance psi to end up at some position x. And so the density at x is just a sum over all the initial particles, and then a delta function that says starting at q, moving by psi, you end up at x. So trivially, you can take the Fourier transform of that. So in k space, you have to calculate the exponential of this psi of q. Now, in one dimension, this psi of q is just Gaussian. And so that expectation value is the integral Gaussian times e to the psi, which you can do by completing the square. I won't complete the square in front of you, but if you do that, you get this very, very simple expression where this sigma squared is just some trivial integral over the linear theory power spectrum. Right? So you just have to do that integral. That's very nice, and that's exact. That's to all orders. And so now if I Taylor series expand that exponential, I'm going to get terms that go as sigma squared, sigma to the fourth, and so on, right? This first term is just p linear. There's a k to the fourth here, so let me write that as gradient to the fourth. Now let me think of sigma to the fourth as sigma squared times sigma squared. Then I'm just doing binomial theorem. I get terms that go as 4 derivatives on one of them and nothing on the other, 3 derivatives on one on the other, 2 derivatives on each. And these coefficients just exactly reproduce the kernel that I wrote down before. And I can go ahead and now do third order and fourth order and fifth order. It's the binomial theorem plus a Taylor expansion of an exponential, right? So you can actually write down the exact expression arbitrarily to all orders in perturbation theory. And the sum, and evaluating any of them involves a single one-dimensional integral. So you don't even need to do mode coupling integrals. It's completely trivial. And so now anyone who comes to you and says, I have this way of doing such and such in perturbation theory, well, I can tell you every single term. I can sum any arbitrary subset of them, and I can do it all numerically with one one-dimensional integral. So it runs in about a fraction of a second on a laptop. So you can go and you can look at all kinds of things. So the first thing you would look at would be standard perturbation theory. And then you go and you look at all of the other schemes that people have come up with. So this is linear theory. This adds what's known as one loop SPT, that expression that I showed you before, which is just second order in the power spectrum. And you can see that one loop SPT, the growth sort of slows, and then if I kept plotting this, it exceeds linear theory out there. I can do two loop SPT, and you can see that this suppression kind of gets partly undone, and then it kind of goes really wonky. And then you can do 5 loop SPT, 10 loop SPT, 20 loop SPT. We kind of get bored around 80-something loops, but you can see that this thing looks to be kind of converging into something nice, but then it gets really wiggly once you go past that point. It really, really blows up. So you can ask, well, that's fantastic. What happens if I go to infinite order? And it does more or less what you would have guessed if you just plotted a nice, simple line through those points. So this is infinite order SPT. And then you can say, okay, so what's the right answer? Right? So I just run an n-body simulation, and it's that. So this is kind of interesting. This tells you that you have this beautifully convergent series, right? I mean, here all of the terms past 2 loop are basically negligible, and yet you're very far off of the true solution. So your internal diagnostics of conversion are completely wrong. And in fact, for at least this 1D CDM-like cosmology, you can actually prove that standard perturbation theories do not describe the evolution on any nonlinear scale, and that has to do with this sheet crossing, which is quite a problem. But you can go further, and you can investigate lots of these other theories, and that's what we've been doing for the last, year or so. We have these great movies that we've posted on our website, so I can give you the link when this paper goes out, which allow you to watch the evolution of these sheets and move around, and is useful for gaining intuition about why these various schemes might actually fail. Thank you. We have a proof that standard perturbation theory and Lagrangian perturbation theory, the solutions are identical to all orders, order by order, which is interesting because they describe completely different physical systems, and that's kind of interesting. There is no such proof in 3 dimensions. We have half of a proof in 3 dimensions, but we can't quite complete it. It's much easier to see the breaking of some of these symmetries that people rely on, and that you can understand why some of these schemes are failing. There's been a lot of work recently on the so-called effective field theory of large-scale structure, sometimes called coarse-grained perturbation theory. It's a standard renormalization scheme often applied in quantum field theory. It's very easy to see what's going on in 1 dimension, so we've been able to correct a lot of discussion, clarify some things in the literature. We have a brand new Lagrangian version of this effective field theory, which works extraordinarily well, actually manages to match the simulations really, really well. And if you specialize even more and don't just do 1 dimension, but you take power law power spectra, then everything is scaling, everything's scale free, and you can just write down all of these things and discuss the structure of the counter terms and have a lot of fun theoretically. And so this is a really fun playground. It turns out there's still some issues in understanding what's going on small scales and understanding the sheet crossing in detail. And where we're going with this paper should be out in a couple of days. The next thing we've been looking at recently is understanding bias, halo formation, and things like redshift space distortions. So let me just finish there. That's right. And in fact, one of the really interesting things is that, the analytic structure is identical to the 3D. I mean, it's really a 3D gravity problem. We've just made the initial conditions 1D, right? So a huge number of things that people talk about that are the dominant physical effect in 3D actually have an almost exact analytic analog here. And all that happens is typically the kind of coefficient of the term rather than being, a half will be, 1.4 or something like that. Yeah. So, yeah. That's right. No, they're not actually. But so we do have. So the reason that the reason that you get that interesting angular dependence in the 3-point function is really a hierarchy of scales rather than sort of angles. And the same thing shows up here in 1D as well. So you still get exactly that same kind of effect. And you don't predict hierarchical structure formation, but you do in the strict sense where everything's just simple powers. But you get something completely calculable, which is nice. Hey, how you doing?
Nice to see you. That's good.
Hi.
One day stuff.
It's been really fun.
It sounds like it.
It's a really interesting.